In this video, we're going to look at Venn diagrams. So this first example here, we're going to consider the different types of shading in a Venn diagram. So first of all, it says at a high school, some students take Spanish and some do not. Also, some students take an arts subject and some do not. Let S be the set of students who take Spanish and let A be the set of students who take art. On the Venn diagram, shade the region representing the students who, and then we're going to look at the different situations. So this first one is saying they take Spanish and art. So this is going to be something like this, Spanish and art, also meaning both. So they have to take both. So in our Venn diagram, the only students that are going to take both Spanish and art are the students that are in this overlap region. So that's the region I would shade. So just so you know, in this Venn diagram, the S here stands for the students who take Spanish. The A stands for all students who take art. So where they're in common is this intersection or this overlap. For part B, it says that they take Spanish or art. So this means Spanish or art. So what this means is really it's everything because they can take Spanish. So everyone that's taking Spanish is in this circle. Everyone that's taking art is in this circle. And it doesn't matter if they're taking both Spanish and art, well, that's still satisfying the condition of Spanish or art because they're taking at least one of those things. So this is basically saying all. And then if we look down at the next one, taking Spanish but do not take art. So this is the same thing as saying taking Spanish only. So this would mean that the shading for the Spanish gets shaded, but not the section that also includes art. And then does not take Spanish or art. So this means not taking either of these. So not in either of these circles. This is on the outside. So this would be considered the complement of taking Spanish or art. Everything that's not Spanish or art. And when we think probabilities, all together in this rectangle would be 100%. And then each of these little subcircles here would be whatever the percent is in the problem. So there could be 50% of people taking Spanish, 30% taking art, and then there's still a percentage of people not taking any of those, with a total being 100. So let's look at some more examples with Venn diagrams. So now we're going to kind of look more at what I was just talking about, those probabilities. So remember, probabilities can be written as decimals, they can be written as fractions, they can also be written as percentages. They all mean the same thing. A total probability is 100% or a whole number of 1. So for number 2, it says a real estate ad in a metropolitan area features the following Venn diagram showing that the probability that a home in this metropolitan area has a garage and or pool. So remember, this total, even though we don't see this rectangle, if we enclose these circles, the total here would be 100%. So the total in this situation would equal 1 since we're talking about decimals. So the probability that the person has a pool, well, we have 0.07, we have a probability of 0.07 that has just a pool and not a garage. And then we have an overlap of 0.05. So we would need to add both of those together. So basically we have 5% of people have a pool and a garage, plus the 7% of people that just have the pool gives us a total of 0.12, or you could say a probability of 12%. The probability of having a garage, so basically the same thing. I have the people that just have a garage, and then I have the people that have both. So I add those up, so 0.84 plus 0.05. Now these calculations are very easy to do, but I definitely think it's worth showing your work just because, again, the more work you show, the more likely you are to receive partial credit because now I can see, well, where did you get your numbers from? And then the next one, the probability of a garage and pool. So this is our intersection, this is our overlap. So this is the 0.05. And then for part D, the probability of a garage or a pool. So the probability of a garage or a pool means, well, remember what we said on the last page, it's everything in the circles. So it's basically all three of these added together. So when we add those together, we get 0.96. Now you might be thinking back to when we did OR before, we used the formula. So when you think back about the formula works because it subtracts off the duplicates. So in this situation, if you just add up these three pieces, you don't have to worry about the duplicates because the duplicates have already been subtracted. The duplicates are really that 0.05. So if I were to use the formula, just so you can kind of see how that looks, so let me just make a note here. So if we do part D, but using the formula, the difference would be you're going to take the probability of a pool, of having a pool, so plus the probability of having a garage. I could have done that in the opposite order, it doesn't matter, minus the overlap, probability of pool and garage. So I've already found all of these probabilities. So if you look, part A was the probability of a pool, so 0.12. So that was everybody that had a pool, plus everybody that had a garage, so 0.89, minus that overlap. So minus the 0.05. So in the Venn diagram, you can really clearly see that everybody having a garage is this category here. Everybody having the pool is this category. But what happened was we counted this section twice. So that's why we have to subtract off that 0.05. And we only subtract off one of them because we still want to include one of those 0.05s. So now when you add up these two numbers and then subtract off the 0.05, you end up with exactly the 0.96. So you get the same answer. So I just wanted to show you that connection. It's an interesting connection. It's doesn't really matter which way you approach it, if you want to use the formula or if you just want to use the visual Venn diagram to come up with that probability. So let's continue. So probability of a garage but not a pool. So that means a garage not intersecting with a pool, so that's going to be the 0.84. Garage, or let me read this again. Probability of a pool, but not a garage. So now I'm in the pool, not a garage, so 0.07. And then neither. So neither a pool nor a garage nor both. So basically the outside. So we have total, these added up to 0.96. So 1 minus that 0.96 tells us that there'd be 0.04 left. So it's the outside of the circles that we're looking at. All right, so we have a couple more examples here. So let's go to the next page. I know we have more pages here, but they're very spaced out. So for number 3, we have a Venn diagram. Again, notice that this one's not labeled for us. So that's going to be really our first goal here is let's get these labels. So you discover a college newsletter from 1976 featuring the following Venn diagram shown below. It shows the percentage of dorm rooms on college campus that have refrigerators and or TVs. So we have 38%, or you can think of that as 0.38. TVs, 53% of people had a TV, or you could think about that as 0.53. Now, when we say the probability of refrigerators versus TVs, we're talking about all of the people having refrigerators, so that means they could also have a TV, and then TVs, 53% of people have TVs. Some of those could also have a refrigerator. So that's what those numbers represent. The 20% down here, this represents the region outside of the circles. So remember, total, everything has to add up to 100%. So our first goal here is really to look at this as, since this is 20%, that really means that there's 80% inside of these circles. So what that means is these numbers in here would have to add to 80%, or 0.8, right? Because 100% minus the 20% is going to give me the 80%. Or you can think of this as 1 minus 0.2 gives me 0.8. So I could also call this 0.8. So now what I need to think about is, well, how do I figure out the overlap? So I know that these numbers, these three numbers that would go here, have to add up to 0.8 or 80%. And if we look at this first question, it says, find the probability that a college dorm has a refrigerator and a TV. So that basically means I need to find this overlap first. And even if that weren't the case, that would be the direction I would go, even if the question didn't ask, because I want to fill in this Venn diagram. So my goal here is to figure out this overlap. So basically, think about this for a second. We know that 38% of people have a refrigerator, plus 53% of people have a TV. Well, that takes us over 80%. And we said that that can only be 80% total. So what that means is that difference is going to be our overlap. So if I add 38 plus 53, I get 91%. Well, 91% minus the 80% that I should have tells me that there's an 11% overlap. Or I can say that if I have 0.38 plus 0.53, that gives me 0.91. 0.91 minus the 0.80 is going to give me 0.11. So that tells me that my overlap here is really 0.11, or 11% of people have both. So this is you can have either answer really, the percentage or the decimal. So now in order to figure out the rest of these, well, if 11% of people, so I'll put 11% as well since I kind of have a combo here. Since 11% of people have both a refrigerator and TV, well, how many have just a refrigerator and not a TV? Well, I'm going to do 0.38 minus that overlap. So that gives me 0.27, so 27%, or 0.27. And then if I have 53% of people have a TV, well, how many of them just have a TV and not a refrigerator? Well, take the 0.53 minus the 0.11, and I get 0.42. So 0.42, or 42% of people have just a TV and not a refrigerator. And if you add these up, it's going to take you to that point. I'm going to actually switch these just so it matches with my decimal. So it takes me to that 0.80. So there you have it. So that's how we fill it in. So then one last thing here. Now we have a conditional. So it says, find the probability that a college dorm room in 1976 has a TV given that it has a refrigerator. So now I have this conditional. So we're looking for a probability of a TV given that we have a fridge or a refrigerator. So out of all the people that have a refrigerator, so given that the person has a refrigerator, so now I'm looking at just this circle. So out of all those people, so out of 0.38, how many of those also have a TV? Well, that's going to be that 0.11. And then we can just reduce this down to a fraction. You could really leave it like that, but it just looks weird to have a decimal inside of a fraction. So I'm just going to simplify my fraction so that I get rid of the decimal inside of it. So one last page to look at. And in this page, we're going to talk about something called mutually exclusive. So if we look at the first problem here, so part A, list the sample space of the outcomes of rolling a standard six-sided die. So a sample space, I'm going to use the curly brackets for my set notation. If I roll a standard six-sided die, your options when you roll, you could get a 1, a 2, a 3, a 4, a 5, or a 6. List the sample space of even numbers. So out of those, how many or what possibilities do I have for even numbers? I could roll a 2, a 4, or a 6. For odd numbers, I could roll a 1, 3, or 5. And then numbers larger than 3, well, that could be a 4, a 5, or a 6 when you roll. And now the question is asking us, are even numbers and odd numbers mutually exclusive? So mutually exclusive means that they have no possible outcomes that are in common. So meaning they're completely disjoint, they're completely separated. So are even numbers and odd numbers mutually exclusive? The answer would be yes, because you can't be both even and odd at the same time. You're either odd or you're even. You're not both. There's no overlap. So in thinking of like a Venn diagram, mutually exclusive would basically be two circles that are never connected. They're disjoint. There's nothing in common. So that's kind of a visual look to it. So for this, I'm going to say yes, because we cannot roll both even and odd at the same time. And if you look at the sample spaces from a sample space point of view, well, there's nothing in common between those two sample spaces. So therefore, since there's no overlap, nothing in common, no intersection, the two events are mutually exclusive. So another way to say this is yes, none of the numbers in the sample spaces are the same. So now let's look at another scenario. So now the next one says, are even and numbers larger than 3 mutually exclusive? So even, we had 2, 4, and 6, and then we had 4, 5, and 6 for numbers that were larger than 3. Well, we have some overlap. Let me just list these off to the side so you can see it better. So even numbers, we had 2, 4, and 6. Greater than 3, we had 4, 5, and 6. So the issue is we have some overlap. We have 4 that can occur in both of those, and we have 6 that can occur in both of those. Therefore, no, they are not mutually exclusive. So now we just write a sentence so we can say no. 4 and 6 satisfy both, so there are both even and larger than 3. So that's one way to answer it. Or you could say no, 4 and 6 are in both sample spaces. So again, thinking of this from a Venn diagram point of view, well, we have an overlap, right? So we'd have 2, we'd have 4 and 6, and then we have just 5 over here. So since there's an overlap, that's why it's not mutually exclusive. So all different things to consider here. So at the bottom, let's write a definition. What is mutually exclusive? So let's just go ahead and write a couple things here. So when two events have no possible outcomes in common. So again, let's draw a picture. So this is event A, this is event B, nothing in common. You can also say two events are mutually exclusive or disjoint. So notice no connection. If they cannot occur at the same time. And that's it. So go ahead and use that new information about Venn diagrams and try the homework problems.